this the other day. Yeah.
So this is something that I really want you guys to know how to control.
Are you talking? How are you?
It's gonna be like the two.
Sorry.
So T double is naturalized to R. So I said my collective integral 1 times e to the R is T. And I got 124,000. So 130, that's close. But I don't think it's close enough. Oh, look, she said. That's what I did.
It's always the hard.
Yeah.
R is T double over
Wait, so is it
2.
Oh wait, hold on.
So 0.2.
3 divided by
I mean, I guess that means that's close, or I'm wrong. Well, like, that's exactly right, though. So R is 0.2. Yeah. Minus 51, right?
now you're 2.
Yeah, I got 131. I got 131,000.
Alright, so most of this. So most of you got this right. So I didn't give you R, and then but I gave you the time it takes to double population size. So you should use the T double formula to find R, and then apply R to the formula to predict population size under exponential growth. Okay. So for today, we're going to continue talking about population growth.
Sounds like
So
a
before
calculator.
we go into a second model of population growth, let's look at some biological examples of when we expect populations to grow exponentially. So here are 2 graphs with examples from real populations. So first is a tree population that colonized an habitat. And when this tree population colonized the new habitat, there was a limited resources there, not that many seed predators, so there weren't factors that could limit births. There weren't factors that could cause extra deaths in the population. So there wasn't anything in particular limiting this population at first. So looking at historical records after colonization, we see this population growing exponentially. Another case results from protection of a population of looking cranes. So these populations were hunted, and then protection was established in the 1940s. And then after that, because this harvest of individuals was not taking place, and the population size was very, very low to start off, you see these numbers were increasing exponentially until 2005. So whenever people manage natural populations, they try to look at these numbers and predict the consequences for when populations behave this way, and thinking whether or not that's sustainable over time, or if this exponential growth of populations will cause populations to crash eventually. So we looked at human population data. So this is just another example here. So we have data over time of human population size, and we can see that more recently, human population growth just exploded, and we see this human population growing exponentially, and we still have this prediction of exponential growth for several years ahead. So if we look at this data, so notice that here we are looking at number of individuals over time. And then I'm going to show you a different way of expressing population growth. So in this case, you see time again in the x-axis, but in the y-axis, what you see is the time it takes for the population to double. So this data is for the human population, and you can see that there is some projection here of change, but at least until the 2000s here, this is observed time that it takes for the population to double. So you can see that over time, it takes less and less time for the human population to double in size. So you can see this projections of human population growth or any other population represented in terms of T-double. And this is very useful in terms of management and health management predictions. Even health insurance is applied, this type of stuff. So think about this data, and interpret this data. Think about what is the implication of this for the overall population growth. So we're talking about dN over dt here.
Population growth? Wouldn't the population growth as the time gets smaller?
Just taking less time for it.
So there's no.
Yeah.
So it's increasing.
Yeah.
There we go.
It's taking us a little longer. That's predicted.
Until the 2000s.
No, and he's like, wait. Exactly.
So it's taking less and less time for the population to double. What does it mean for the population growth rate?
It's a little messier. Because yeah. The problem that
All right, let's pause. Okay. So also we got this right. So if it takes less and less time for the population to double in size, it means that the population growth rate is increasing over time, which is what we observe in populations that are growing exponentially. Okay. So when you compare models of population growth, and when you look at predictions of population size over time, we discussed a model in which resources for growth are limited. So it means that this is kind of the perfect situation for populations. So there's nothing limiting population growth here, at least for the time projected. However, in natural populations, most of the time, growth is limited by several factors. Very often, you don't have enough food, you don't have just basic enough space to hold this many individuals. So you're going to see populations growing until a certain point where they can no longer grow because the environment cannot support all of the individuals. So whenever this happens, this can be represented by another model, which is called the logistic growth model. So the logistic growth model, which represents population size over time, and here it's very important that you pay attention to the axis of these graphs and what they represent. So here you have number of individuals over time. You have this S-shaped curve in which at first you observe the population grows, and it looks very similar to the exponential growth. And it grows very fast until growth starts to taper, and then it starts to stabilize at a certain population size value. So this is the basic prediction of how populations will grow if resources are limited. So this is the logistic growth model. So if resources are limited, you expect that the environment at a given time, a given point in time, can only support an X number of individuals in this population, right? So this number of individuals in the population that the environment can support is called the carrying capacity. So the carrying capacity is the number of individuals, so it's expressed in number of individuals. So it is the maximum number of individuals that the environment where that population is occurring can support. So we can see that if there is no limit, populations grow exponentially. If there is a limit in terms of number of individuals the environment can support, the population grows until it reaches the carrying capacity, and then population size remains constant over time. So it tends to stay at the carrying capacity over time. So if we think about just the environment as just being space. So look at these boxes here, this shaded area, as the carrying capacity available for this population to grow. And then look at these squares as individuals filling that carrying capacity. So if you look at this graph of number of individuals in the population over time, and look at the beginning here, so initial points in time, you'll see that the carrying capacity is not filled completely. So you have way less individuals in the population than the environment can support. So you have a lot of potential here for the population to grow. And that's exactly what happens. So the population will grows fast, and it grows fast until it reaches half the carrying capacity. And then after it starts to get closer and closer to the carrying capacity, you can think that things start to get very crowded, resources start to get limited, individuals in that population start to compete for resources. So you're going to have deaths associated to competition and resource limitation. Then you can see this growth tapering off very close to the carrying capacity. So if you look at the population size at the carrying capacity, you can imagine that individuals are filling all of the space that the environment has to offer. It's just kind of an analogy that I think it helps for you to understand visually what the carrying capacity means. So we can express this growth rate in here, so pay attention to this. I'm not talking about projections of population size. With this formula, I'm talking about growth rate of the population. So this is the formula that we use to predict growth rate over time under the logistic growth model. So looking at this formula, I'm just going to add all of the explanatory components here. So we have dn over dt, which is that growth rate at a very tiny slice of time. R, which is the intrinsic growth rate. So we know that R is a property of the population. So this R does not change over time. N is the population size. And then you have this entire term here, which takes into account the proportion of the carrying capacity that is being filled by individuals in this population. So K here is the carrying capacity, and that's expressed in number of individuals. So let's say that you have a carrying capacity of 100 individuals in the population, and then you have one individual in this population. You still have a lot of the carrying capacity that can be filled, so you can expect that this growth rate is going to be very high. The interesting thing here is that if you cancel out that term with the carrying capacity, you have a model that is exactly how you predict rate of population growth in the exponential growth model. So we can assume that that term here, so this term is indirectly assuming that births and deaths, they are dependent on the number of individuals in the population, and that's implicitly included in this model through this term looking at the proportion of the carrying capacity that is filled by individuals in a population. So think about this. So if the number of individuals in this in the population approaches the carrying capacity, this whole term here is going to be 0, which means that growth of the population will be 0. So it means that the population will stop growing when it reaches the carrying capacity. So if this number is a lot different, it's a lot smaller than the carrying capacity, we can imagine that the contribution of this term to the whole formula will be very high, and then you're going to be looking at a very fast growth rate over time. So we're going to be doing exercises in the worksheets to look at how DMDT varies with population size. So first, let's do some applications here of this formula. So notice that I'm putting a hint here. In the exam, there will be no hints. The hint here is just so you know how to solve this problem for the first time, where you're expected to know moving forward without the hints. Look at what the question is asking you.
I got DN over DT.
I'm not asking you for DN over DT over here. I'm asking you
After you get the rate,
DN over
so that's how like the population's increasing. So you have a population, then you have how much it's increasing by. So you just add them together. So that'll be how many people are in the population. You're not supposed to get
Yeah, boys got the rock.
yes. Minus 4 over 100, which would come out to 0.96 times 4.8, which would give you 4.6, and then you add that to 4.
So 8.6.
8.6.
So we're at.
Does that make sense? 8 to 10.
I just.
So, and then, or in this question, it's not asking your rate by millions, it's asking how much. So you get how much is increasing by, then you're just going to add that to it.
4.6.
Okay. So most of you got this. Fantastic. So you have to apply DN over DT and then sum the initial population size to the number of individuals that were added to the population. So now there is something else that we can get in terms of information out of this first. So we know that looking at the timeline here, so this is generations over time, population size, number of individuals. So look up there how the carrying capacity is expressed in the number of individuals that the environment can support. So initially, dN over dt, we're going to increase very fast until it reaches, the population reaches half the carrying capacity. So at this point, when population size is half the carrying capacity, is when population growth rate is the highest. It reaches its maximum at k over 2. Past that point, population growth rate will tend to decrease until it reaches 0 and the population remains constant over time. So dN over dt will increase. It reaches maximum point. After maximum yield point, it will decrease until it reaches 0. So after this point in time here, the population will remain in the carrying capacity. So no new individuals will be added like extra of that rate. So you see no increase in population size past the carrying capacity. You can understand this more clearly when you do the worksheet, but this is an important point of this model. So we can make some inferences here just based on the population size in comparison to the carrying capacity. So whenever population is down here, we can assume that the population is much smaller than the carrying capacity. If it's around here, we assume that the population is about half the carrying capacity. And as it stabilizes growth, we assume that the population is the same size of the carrying capacity. Okay. So concept check.
I thought
also asked when is the population growth rate the maximum value, so we have the carrying capacity. All right, so there is application on that.
Okay, so you're kind of, so you have the equation, right? So the logistic equation, and you're giving me which is 500, and then you're telling me that maximum population growth rate, that's whenever it's 0. So if you take 500 divided by 2, that's your n, so then you're just putting that into the equation. Does that make sense? So you'll take r times 250 times 500 minus 250.
Yeah, it took me a while. I had to like do the whole did it wrong. I wanted like 25. I'm like, this is incorrect. And I skipped the whole like okay. And I was like,
Alright guys, let's go here. Okay, you did great here. So I asked you for the maximum, the population growth rate at the maximum yield point. I gave you the carrying capacity. So you have to figure out what population size will be, so that's half the carrying capacity, and then use the formula to find Tn over T. Fantastic. So logistic growth rate, I mean, it looks amazing, right? To think that populations will stop growing whenever they reach the carrying capacity. So now I just want to show you some examples of what happens actually in reality with populations. Usually, you'll see populations growing, reaching the carrying capacity, and actually fluctuating around the carrying capacity. And that's because usually it takes a little bit of lag of time for the population to respond in terms of, okay, there is resource limitation, so it's going to take a few generations for that to kick in terms of increased death rates and reduced birth rates in the population. You can also think about these populations as the population having some sort of inertia. So if it's growing, it's not going to stop growing right away when resources are limited. It's going to take a little while for it to temper, it grows, and then go back out around the carrying capacity and down back again. So when we think about R and K strategies, when we think about life history strategies, and we think about the number of offspring that a given species will put in the environment at a given time, given point in time, we can think that our strategies, they are more prone to overshoot their carrying capacity than PK strategies are. So because imagine that the population is growing, so for every single generation, those individuals are putting just thousands of offspring out. And it's going to take a few generations for that to kick in terms of death rates and decrease the birth rates. So our strategies, they tend to overshoot like way more out of the carrying capacity and then die back tremendously and have oscillations around the carrying capacity. And this is mostly caused by this inertia in population growth and the time that it takes for the population to respond to resource limitation. So here is just a comparison between R and K strategies. So you expect that the red curve is a curve that corresponds to a species that has R strategies. So they will tend to produce lots and lots of offspring at once. So they tend to oscillate tremendously around the carrying capacity. And then the blue curve represents a K strategist. So fewer offspring at any given generation, and it takes longer between generations. So usually they will oscillate a little less around the carrying capacity. So some real data to show you this. So this is the document. This is a crustacean water flea. So this is a fish of the logistic curve. So population growing, reaching the carrying capacity. So this is what you would expect based on the model. And then the points refer to the actual data related to this population. So you see the population overshooting, dying back, and then oscillating around the carrying capacity. Whereas if you look at a K strategy, so this is a mammal, a sea lion, you see the population is more around what is expected for the logistic growth model. There is some oscillation here, but it's nothing compared to what we observe in our strategists. Okay, so what causes this limitation that we observe in the logistic growth model? So we can think of factors that can limit population growth, and we can think of these factors as being density dependent versus density independent. So when we think about density independent, it means that it's going to kill or it's going to limit births independently, regardlessly of the population size. So you think of natural disasters, for instance, earthquakes, volcanic eruptions. It's going to kill a bunch of individuals, whether it's a small population or a large population. If you think of density-dependent factors, here we are more looking at factors that cause mortality or reduce birth rates that are related to biotic interactions. So outbreaks, for instance, of the diseases or pathogens that involve interactions between hosts. So those are density-dependent factors, for instance. Competition, density-dependent factors. The more individuals you have, the more they will compete for resources. Predation is another one. So if the predator has a ton of prey, is going to just exploit that prey probably to extinction. And we're going to look at these interactions next week. So you can make these comparisons between density-dependent and density-independent factors regulating population growth. And here you have all of these examples are examples of density-dependent factors related to biotic interactions. So here you have a competition for space. Here you have density of females reduces clutch size. So you have an effect on the success of the offspring. So probably some resource competition here. And again, with plants, the same idea here. Could be resource, could be space competition, could be a pathogen that strikes very dense populations as well. So this is a really cool graph showing you the causes of death for the past 100 years in the human population. So you can see that there are some really striking cases that stand out. So this flu event here was one of the largest flus in the world. This is a flu in China in the 1930s. This is the flu epidemic, 1918. Several drought events over time. So looking at these cases, just think about density dependent and density independent factors. You want a point? Okay, so look at fluid and earthquake, landslides, so these are all abiotic events, so they're density independent. Epidemics, on the other hand, so the highest is the population size, usually the more drastic impact. Good for you. Yeah, 100% of you got it right. You're so smart. Okay. So worksheet time. So let's look at population growth rates over time and practice the formulas of those growth.
Mindless.